Hi everyone, in this video I will go through an example for the disturbance rejection of the closed loop system. So here we have the system. As you can see, there is the reference signal, the disturbance, and although it's not shown here, but we would have a noise signal, sensor noise signal added to the system here. But in any case, we assume that the noise is equal to 0, so there's no noise, and the only input to the system is the disturbance, or d prime of d. And we want to find out the steady state error in case d prime is 2 for t bigger than or equal to 0, for gp1 given as 1 over 1 plus s, and gp2 given as 2 over s. And in cases where gc, the controller, is equal to 1, or it's equal to 1 plus 10s times 10s over s. So let's start doing it. If we set R and also N to 0, this will be the resulting block diagram for the system. D prime GP2 C here. Then we will have these two transfer functions, GC and GP1, with their negative feedbacks here. And in such situation, we can see that if R is equal to 0, setting R equal to 0, then the E will be equal to minus C of t. Okay, so this is something that we have. As a result, the steady state error will be equal to minus steady state value of the output. So we can find out the transfer function from d prime to c. C will be given as gp2 over 1 plus gp2 gp1 times gc, the controller, times d prime of s. We already have values for gp1, gp2, as you can see here, and let's assume that gc is equal to 1 for the first case. So case number 1, gc is equal to 1. As a result, c will be given as gp2 2 over s over 1 plus gp2 2 over s times gp1, which is 1 over 1 plus s, times d prime of s. And we also know that d prime of t is equal to 2 for t bigger than or equal to 0. As a result, d prime s will be equal to 2 over s. Now we can say that steady state error, which is equal to minus steady state value of the output, can be written as minus this here, can be written as minus limit of c of t as t goes towards infinity, which is equal to limit of s times c of s as s goes towards 0. And again, we can rewrite it here, is equal to minus limit of s times c of s is this transfer function times d prime of s. So we have, if we just simplify it, we will have s times 1 plus s plus 2 in the denominator, and in the numerator we will have 2 times s plus 1 for the transfer function times d prime of s, which is 2 over s. And you can see here that these S's will be cancelled out with each other. As S goes towards 0, we will have steady state value of error equal to minus 2 times 2 of 4 over 2, which is equal to minus 2. So for GC equal to 1, the steady state error is equal to minus 2. Now let's take the second case into account. In the second case, GC of S is given as 1 plus 10S over S, 1 plus 10S over S. We can form the C of S again, which will be this transfer function GP2 2 over S over 1 plus 2 over S times GP1 1 over S plus 1 times GC, which is this time 1 plus 10S over S times the prime of S, which is 2 over S. So now we can write steady state error is equal to minus limit of S times C of S as S goes towards 0, and this is equal to minus limit of S going to 0, C of S, which is the transfer function times 2 over S. This S here and S here will cancel out. And for the transfer function, we will have S squared times S plus 1 plus 2 times 1 plus 10S at the denominator. And at the numerator, we will have 2S times S plus 1. And you can see here that as S goes towards 0, the steady state error will become 0. So for the second controller, steady state error is equal to 0. For the first controller, steady state error is equal to minus 2. This is what we need to do for the first part. And by looking at this example, we can find that there is a connection between the entry point of the disturbance and the effect of the integrators in the system blocks on the steady state error. So we can conclude that if the disturbance enters the system after an integrator, then the steady state error for the step input, here the input is the disturbance, will be equal to 0. Or we can say that this is similar to the case in which we are dealing with a type 1 system, for which we are supplying the step signal as the input, and in that case the steady state error will be equal to 0. If there is no integrator before that, the steady state error for the step input will become some finite value, and so on. So you can try this by using some other examples maybe. Okay, so that's all for this video. I hope you have enjoyed it, and you could compare what you have got on your own with the result that I have presented to you here. Thank you for watching, and see you next time.